significant. And so it can play a role, and people have worried about how to separate these different orbitals, particularly the group in France has done so. So there's been some extra work done on it, trying to deal with the real complexities of the system. We went on to look at dynamics, which I'm going to show you next time, but we didn't eventually try to do a movie of the orbital change. There's a number of questions, so I'm sort of stopping to simulate questions, and I'll go back here.
I have two concerns. So first, when you say you measure the electrons, you measure the function.
Excuse me?
You say you could measure the wave function. But wave function is not actual length. It's more like mathematical description, and you say you can represent it in such a way. Is that some contradiction?
I mean, I think there's also a good, so I argue you measure the wave. Of course, it's not one molecule in that measurement. You measure multiple molecules to get a harmonic. You would not get a harmonic spectrum from one molecule. You would get, if I made a measurement, so a harmonic would be some frequency, I guess. So I have a gas of atoms, and we try to make the phase matching as benign as possible. So this is an amplified version of the single atom response. We've done many experiments to confirm that, but it's not one of them. So maybe that's also, I should be careful about that. I think when you look at it, you have to think of it that way.
This is.
I get many people now. So of course, I'll be very careful.
Yeah,
Right,
this is what I wanted to say. It's not really, what you have measured is not a single electron wave function. You've measured the density operator of a large ensemble of systems, which you very, very carefully prepared in a way that it's essentially in a pure state, right? But it's always what tomography does, and I don't think that anybody would fire you for that. I would not.
But at least I have the phase. I do
Yeah, you have the phase. But people like Serge Roche who does tomography of photons.
Yes.
It's kind of the same idea.
I think I agree.
Yeah,
I agree.
it's beautiful.
I don't see the problem in the sense that your measurement in this case is on harmonic generation. And you need, as someone back there said, you need some model
With you,
that relates
it was
the
a
initial
second
state
point. It
to
wasn't,
what you measured, the harmonic
and we
generation.
do with your point.
And if you formulate things in such a way that you show the influence of the initial state on what's measured, in some sense, that's a description of the initial state.
So I don't say what Hossein said. I don't have a problem with the experiment and the data. I think all the question is the interpretation stuff. And I think, frankly, part of the problem is you stated a little provocatively when you say you measure an orbital. If you came out and said I measure a Dyson orbital or something like that, I think probably there would be less issue, because Dyson orbitals have a clear definition, and it's an orbital, but not in the normal molecular orbital sense that you talk about a Hartree-Fock orbital. My problem with the statement that you measured an orbital is orbitals are unmeasurable. I will say that unequivocally if you're talking about a Hartree-Fock orbital. First of all, there's many reasons why, because that orbital is not a well-defined thing, first of all. Which approximation did you calculate the orbital in? Real systems are multi-configuration, so it's, which is fine in the Dyson orbital picture, but not by itself. And of course, you can always take unitary transformations among the set of orbitals in a single Slater determinant, and that's unchanged. So those orbitals aren't well-defined things. You made arbitrary choices, and we never measure arbitrary things. We never measure things with arbitrary choices. So. But I think measuring the wave function or any wave form is fine as long as you have a reference that you know, right? And I mean, that's what you've done here. You said you knew the plane wave coming back, right?
And it's phase related to its start.
Yeah, you're beating it against a known wave function or against a known waveform. I mean, you do that to measure light fields too, right? So.
Okay.
Right, I mean, I would agree with Fred. I mean, you have it because everyone would agree that there is a wave function for the molecule. We'd all agree that we don't know it, but we would all agree that up to an arbitrary phase it exists. And then you do this well-defined thing. You integrate out n minus 1 of the electrons, and then pretend you know the reference, right? To some approximation, right? So I guess I have a version of though. Why has it persisted to talk about measuring orbitals rather than, in other words, is it because of the phase? Do you know what I mean?
You mean why is it a controversy? I don't think it's.
I mean, is it useful to stick with thinking about orbitals because you do measure a phase difference, right?
Yeah.
I mean, you measure a thing that has nodes in it.
Yes.
Right.
Yes.
And then you, from your tomographic reconstruction, you can say that there's a phase jump across there, right? And that seems to fit very well with the orbital picture. So I guess my question is, how do I think about that phase jump in the Dyson orbital? What meaning does it have?
You're thinking about the phase jump between one
Yeah,
side here,
yeah.
one side and the other side?
Yeah.
Well, I would have thought that just comes out of the Dyson orbital, the difference between one and the other. I mean, I've never done the calculations.
Well, I think the simple way to make sense of it is just to think of the single configuration approximation. Because in that case, the Dyson orbital is the HOMO. But of course, the Dyson orbital for the exact wave functions is not just simply the HOMO. So I think
But it would have that same phase relation.
the exact one I don't know, but in the approximation of the single configuration, it would just be the HOMO. Yeah.
I'll go ahead. Oh, we've got one more.
Can you give a clean definition of what a Dyson orbiter is? Because I've never heard of it.
Well, again, I'm not a theorist, I'm an experimentalist, so these guys will give you a better definition than I will. So they can correct me if I'm wrong. I think of it as the n electron wave function minus the n minus 1 electron.
But then it's different terms.
The difference between the two.
How can we
You
take
project out to n minus 1. Pardon?
How can we take the difference between two wave functions that live in different units?
How do you do it? How do you do it experimentally? I think that's the way. How do you do it theoretically? I'll point to the people in the back of the room who will
I
probably.
will write it on the blackboard.
Okay, there it is. I got the right person. He's got the right people here.
If the marker works, yesterday they worked, so it's this thing here. So we have an n electron wave function and an n minus 1 electron wave function. And this symbol here means integrating out n minus 1 electron. So once you have done that, you have the Dyson, which is the 1 electron. And if you arrange the Attosecond, this is represented by a single slate determinant. You remove the valence orbital, and this is represented by, in the same unrelaxed Attosecond, by all the other same orbitals. So this would just give you, in that case, in Attosecond, this would give you unrelaxed Attosecond, so to say, it would give you the HOMO.
So, I mean, very nice is beautiful description, definition. I mean, it's clear that you have the experimental data, but the interpretation, what you're measuring in terms of electron wave function is based on some theoretical approximation, as Brett and others have said. So it's very linked to the theoretical formulation that you put into the experiment.
Yeah, I think, can I come with one comment?
Of course.
I think this is,
may only have
for
to
me,
talk about
I think, I don't know, I mean, now, for the students, you see, now this is really elevating people, or animating people to discussion. This is very great, and this is why this paper, this work, is a key work to know about. Because it's been extremely influential, and if you stay in this business, you will hear about this from time to time in your career. So you all have to study this paper, and you have to think about what is wrong and what is not wrong, and if there's something wrong, and make your own opinion. And I think all of us more senior guys have our opinion, and we can tell you about that also after this talk.
One more, and then I better go ahead. Also, I've got nothing more. We'll have to stop right here.
Okay, so let's say that dicing methodologies. So I agree with the mathematical definition, but presumably the dicing orbitals constitute an infinite Hilbert space. And when you measure it, you have only a finite number of measurements. So every time you measure it, you collect the wave function of dicing orbitals. Then how do you reconstruct dicing orbitals?
Well, I would not say we started out to reconstruct a Dyson orbital. We do a tomographic reconstruction from the data I showed you. So we know nothing about, when we did this, a bunch of physicists, we weren't really into Dyson orbitals, I must say. We just saw it almost in a single electron behavior. But of course, immediately confronted with this issue, what did you really measure? So we did tomographic imaging. It just uses tomography. You saw the data. You saw the arguments, even the approximations we made. I've discussed, and they've been filled in since then. But I've discussed the approximations that are in the paper. So we knew nothing about Dyson orbitals, nor did we have that interpretation. I think by the time the paper, we did the interpretation in the paper. But that's just words you put on top of the tomography. Okay.
Can you do this for hydrogen atom, something
Excuse me?
Can you do this for hydrogen atom, something you cannot?
Well, I couldn't turn a hydrogen atom around, so but of course I could see a spectrum, and maybe I could. So I can't do it. I can't do a tomography. We started out. Let me try to tell you what we started out to do. But actually, maybe I wanted to stop and make a statement in between. So I think I wanted to make a comment. So I thought that it's interesting to think about the relation that's been done here in high harmonic spectroscopy with photoelectron spectroscopy. In photoelectron spectroscopy, you bring in a beam, let's say an XUV beam, and you photoionize, creating an electron in the continuum. It's a photoelectron replica with encoded molecular information in it. And it's, anyway, it's of the XUV pulse. So the information on the molecule is encoded in it. In high harmonic spectroscopy, we do just the opposite. We bring an electron back again. We make a transition moment back to the ground state, an inverse process, and we make a photon replica with encoded molecular information in it of the recollision electron wave packet. So these are very similar processes, just one going one way, one going the other way. Now, of course, to say that they're similar, there's also the tunneling and propagation, but you might say both of these are kind of boring processes. And so the only interesting process in this regard is the returning electron. So there's a deep connection between the two. If you want to look at the differences, high harmonic spectroscopy measures photons, not electrons. Phase matching, not space charge, gives you the limit to how many charges you can have or how many molecules or atoms there could be there. In photoelectron spectroscopy, you get one or two and the electrons start to repel each other. We heard that in the diffraction work. Here you can have 10 to the 5, 10 to the 6, 10 to the 7, 10 to the 8 photons, and it's okay. Electron exists on the continuum for only a short time. High harmonic spectroscopy is highly multiplexed. Multiple frequencies are produced simultaneously. It would take you forever to do the similar experiment by photoelectron. It can borrow all of the processes and the power of coherent optics. And we're actually using it here because we're putting many atoms together coherently, as if we were doing the experiment on the planet. And optical methods can remove a great deal of space-time averaging in here. I didn't show you that, nor have I made the case of it. However, there's a large field present in high harmonic spectroscopy. That said, what you're competing with, which is some sort of photoelectron or femtosecond experiments, often are relatively strong fields also. So, you know, because when you have a short pulse and you want to do something, you need high intensity because there just aren't many photons. So we're not that far above as a whale-like experiment, really. Energy conservation can't identify final states as you can in high harmonic spectroscopy. And only weakly bound orbitals are visible, and maybe we have. So those are differences, and I thought it was worthwhile stating them. And let you think about the connection between what we're learning here and what this whole field of photoelectron spectroscopy is. I'm going to go on to chemical dynamics, and I suspect I won't have time for solids. You give me guidance and how to go. Okay, so I think it's natural to go on and say, can we do something in dynamics? Our vision when we started out was right after tomography, and we said, okay, let's see if we can do a movie. We can make a tomographic movie. By the time we got all the data to do it, and we have beautiful data everywhere, we gave up on the idea because of multiple orbitals, and as molecules move around over potential surfaces, orbitals are coming together, and we thought we couldn't keep track of what orbitals were where and what was contributing. So we didn't do it, but we made, I think, beautiful progress, and it's a direction first. So let me first start out with the problems. A couple of you brought it up to me in the first place. We said, let's take bromine. It's a simple molecule. So even physicists like us, like me, can understand bromine. Let's do the easiest thing we can. Let's take bromine and photoexcite it to the excited state. And we will choose the state that just directly dissociates into a fragment. So this is going to be the most boring chemistry you can imagine. The molecule just comes apart. But immediately you have a problem. Immediately you know that you can't excite very much from the ground state to the excited state with a short pulse. Again, it's the issue that as you make the pulse shorter and shorter and shorter, its intensity grows and grows and grows. And pretty soon you have no photons unless you get the intensity higher than you would like. And so in order to control the excitation so it goes to where you want and not just somewhere up there into the sky, you have to keep the intensity in balance. So in this experiment, we started out by doing some, just checking out to see how much we can put and still know where the population went. So 10% is the maximum. So we excite 10%. So how do you possibly identify the signal from these few dissociating molecules in the presence of a strong field against all other possibilities ionizing, for example, from the ground state or something like that? So photochemistry has always dealt with this problem, or in solids, all short pulse experiments have always had to deal with this problem. And they almost always use something to do with resonance, some way to do it. But here we lose it because we're making harmonics or a continuum. Harmonics are harmonics, so there's no frequency information on the level of the state. And if it's an attosecond pulse, it's a continuum. It's even worse. So there's the experiment again, put in potential curves, potential energy versus separation. We photoexcite, the molecule begins to separate. When we think we want to look at it, we come on with an intense pulse and we ionize it to the ion and look at the high harmonics. So we look at the high harmonics created, so we bring out the electrons back and ionize it again. We do it. What will be important is to think about the phase. Remember that the phase the electron accumulates after it leaves the atom and before it comes back again, during the time its trajectory, is the action integrated along the path it takes, plus the difference in the ionization potential, or the ionization potential. So the clock starts ticking from the ionization potential. If your clock is at 0, the clock is ticking here, and the clock is ticking here. If there's population ionized from both here and here simultaneously, they both will have a ticking clock, but the ticking clock for the ground state, the level from which you took the electron will be different, and that difference is the delta phase, delta ionization potential between the excited and ground state. And that builds up significantly. For the molecule like bromine, it's 2 to 3 eV. And the time birth to recollision varies on the order of a femtoseconds. And so the phase accumulated is a few radians. That's important. That's a significant amount of phase. So when we came to do the experiment, here's what we see. A pump pulse at time t equals 0, and the probe pulse at some time, shown there, time delay in picoseconds. And here we see harmonic 13, 15, 17, 19, 21, and 23. And there's the time dependence. You can see the harmonic signal fell, and it fell sometimes almost by a factor of 2. Now that's amazing at first glance, because we put levels in the high state. You might have increased the ionization probability. But we only put 10% at most in the excited state. So how could we get such a big modulation? Of course, it's that phase I described to you before. The electron from the excited state accumulates phase. The electron from the ground state accumulates more phase, and we have the same frequency but different phase. So, that's the blue ones. The red are the even harmonics, and they're caused by the excitation pulse. And so that's really a clear marker of the overlap. There is a time when the excitation pulse and the ionization pulse are simultaneously present, and they lead to even harmonics. But it's only in modulating the electron and they continue. So the seeming disadvantage of having the potential for ionizing from both has gone away, because we can use the ground state as a reference and do a homodyne detection system. So that's probably potentially possible in any of these short pulse and attosecond-like experiments. You ionize from a couple of things, and if they're coherently related, this is a local oscillator on which to reference. However, we have amplitude and phase mixed in this experiment, and can we get rid of it? In order to get rid of it, we go back to what I talked about last lecture. I talked about trying to bring in some of the techniques from ordinary perturbative measurements, in this case, transient absorption spectroscopy. Or transient, not absorption, but transient grading spectroscopy. So we said, let's bring our excitation pulse in at 2 different angles. So the excitation then is in a, well, you can see it if you're close enough to the front, I don't know if you can, but illustrated here is the grading that's caused by the crossing of the excitation beam doing the exciting of the molecules. In some places, we have constructive interference and the molecule dissociates, only 10% of course. And in other places, we have destructive interference and no molecules dissociated. So we made a pattern of dissociating and non-dissociating molecules. So that's our pump pulse, t equals 0. And we come now with our probe pulse, which is going to generate the harmonics. And we should see the harmonics diffracted. If you think about the diffracted radiation, which is illustrated here, I'll show you in the next view graph, the amplitude and phase contribute differently to the 0 and first order signal. And so for every frequency, we have a 0 and first order signal. We have 2 measurements and 2 unknowns, amplitude and phase, 0 and first order. So we have amplitude and phase information simultaneously available to us. It becomes a fully coherent spectroscopy at this point. Okay, so here is the results. I thought I had the diffraction, but you can see this is really directly out of the experiment. Not presented for you to see well, but I think you can see that there's diffraction, even in this poor image there. So this gives you then access to the amplitude of the transition moment and the phase difference between the transition moments. The amplitude of the transition moment from the excited state as a function of time relative to the fixed ground state, just to make it clear. And also the phase of the transition moment as a function of time minus the phase of the ground state transition moment. So that's what we have available to us. When you look at this figure, there's a number of very interesting things that you immediately see. You see that in all cases, for the amplitude of the transition moment, there's a rapid fall and then a rise, a rapid fall and then a rise. And you can look at that by scaling them all to the same scale as they're shown in that inset or shown in this inset. And you will see that each harmonic has a different minimum time delay, progressing harmonic to harmonic to harmonic to harmonic. The highest harmonic is the one that's in closest. The lowest harmonic is the one that's at later time delay, in all cases. I'll show you why that is in a moment, and then but I want to also comment on the second thing. There's not so much interesting in the phase here, so I'm not going to comment too much on the phase as a function of time. But there's something kind of interesting, and you probably saw it immediately here. On the second of these, what's the difference? It's illustrated here. The bromine molecule that started out as one molecule and photodissociates either perpendicular to the direction of the electron recollision, or it dissociates parallel to the direction of the electron recollision. We can choose that by the polarization of the excitation pulse. It's a perpendicular transition. So it's not quite as clean as I stated, but it's approximately as I stated. So you see immediately here the disruption of the amplitude of the transition moment in this case. You can see the amplitude of the transmission moment is very well behaved here, and you can see that it has an abrupt change here in all harmonics, and you can see that it's sort of abrupt. It says this very low value where it seems to be distorted. It's a small transition moment, smaller than it would otherwise be in that case. So what's the cause of that? That's easy to deal with, and I want to talk about that first. So the electron could leave, as the molecule is now dissociated into two components, the bromine plus a bromine atom. It could leave from this atom, go out that way, but it sees something in its way. It's disrupted, and therefore it will not come back and recombine as well here. Of course, it could leave here and come back. Of course, it doesn't mean all signals are destroyed, but it's the phase of the electron is disrupted, at least to a certain extent. And so the emission of the harmonics are suppressed somewhat for that reason. So that's the first thing I wanted to comment. Now I want to go back to the second part and show you the second part. When the ionization occurs from a dissociating molecule, the dissociating molecule goes through different separations as a function of time. And as it goes to different separations, it will get to a place where there's a wavelength and a half, or two wavelengths, or three wavelengths between the two atoms that are there. And so there's a potential for destructive interference when this occurs. Radiation from one and radiation from another atom are out of phase, and we should see that, and we do see that in the decrease in the signal. If that is the case, then the wavelength for longer wavelength light is a longer wavelength electron, and so we should require the atoms to be more separated for the minimum, for the destructive interference to occur in the case of the longer wavelength electron. So in other words, the photon is giving us information about the electron that's doing the real experiment here, and it's telling us where it went, telling us about it. We can calculate the dissociating atom and calculate where the wave packet is as a function of time. And that calculation is shown here on the line, and the harmonic minima are plotted here relative to that line. You can see that it fits well. This, I believe, is pump probe delay. So longer delay, longer wavelength, as I said before, because the atoms are more separated. And so we're essentially doing an interferometry on the molecule, an electron interferometry, the distance between the two atoms in the molecule. Okay, so that's the second thing I wanted to talk, that's just the second thing I wanted to talk about. So we have a fully coherent spectroscopy, And since then, we've extended it further. We now measure the amplitude and phase of the ground state of the molecule as a function of angle,